Welcome to EDU World Space.
This is chapter 21, problem number 78. This is about a sock and a sweater that is put in the dryer and that are stuck to each other. In the problem, we're given the mass of the sock as 40 grams, and we are told to assume that the sweater is like a sheet of charge. Let's say this is the sweater, and the sock is actually clinging onto it, right? Due to the electric interaction between the two. And that interaction is overcoming the gravitational force acting on the sock so that it is causing the sock to still be stuck to the sweater. So then the electric force acting on the sock has to be in the opposite direction so that the net force acting on the sock would be equal to 0. From here it means Fe is up, right? Minus Fg, they're equal to each other. Well, let's not write it in the vector form. Let's assume that positive y is positive and negative y is negative direction. So Fg is in the negative y direction. That's why we have the negative. So overall from here, the electric force has to be equal to the gravitational force at least. So in the first part of the problem, we're asked to estimate the minimum attraction force between sock and the sweater. So we're asked the minimum Fe. The minimum Fe, as you see, it has to be equal to Fg, which then equals m times g, m sock, right? So m sock would be 0.04 kilograms times 9.8 meters per second square. So from here, it's almost 0.4 newtons, all right? This is the first estimation. And then it's asked, what is the charge that is generating this sort of Fe? We are asked to estimate that, the charge Q. How are we going to do it? Again, it's given in the problem that we should treat the sweater as a sheet of charge that, let's say, has Q charge distributed over an area, right? So we're going to define a sigma charge distribution because we know for the sweater, the electric field that it generates is sigma over 2 epsilon naught, right? The sigma being the surface charge distribution here, Q over A, 2 epsilon naught A then equals to sigma over 2 epsilon naught. Now, if the sock is interacting with this electric field and it has the same amount of charge, again, this is given to us in the problem, then the force, electric force acting on the sock has to be equal to the charge of the sock times the electric field of the sweater that we just calculated. So it's Q over 2 epsilon naught A. Then from here, Q squared over 2 epsilon naught A is going to give us the strength of the electric force. Then this also, we know that equals to gravitational force if the sock is levitating, which is mg. Now let's copy this equation. Q squared over 2 epsilon naught A equals m times g. From here, then Q squared is mg 2 epsilon naught A. If we take the square root of both sides, then we're getting Q. M is 0.04 kilograms, right? G is 9.8 meters squared. Meter per second squared. That's the rotational acceleration, right? Meter per second squared times 2 times epsilon naught is the permittivity of free space, 8.85 times 10 to the negative 12. So coulomb squared per Newton meter squared. And the area of the sweater, we're going to use an estimate here. So let's assume that it is like 0.1 meter squared. It's almost like a square feet, okay? So it's 0.1 meters squared. Then we're going to find, let's not forget to take the square root of everything. So we're going to find the Q to be 8.8 times 10 to the power of negative 7 coulombs.